Right, so here I would like to acknowledge the ever-growing Decadal team at IPSL. So when we started this project, for 5 years back, we're just Juliette, Didier, and myself, and now there are, we have more and more people, both permanent people and postdocs and students going. So it's quite exciting. And so here I want to acknowledge a number of, kind of new colleagues joining in the Decadal gang. And also, Pablo Ortega was a postdoc with us now in Reading at NCAS Climate, working with John and others. Sulagna Ray, who's now at GFDL, and Sebastian Nguyen, who's one of our engineers making all these runs, basically, which is so precious. So, right. So the topics I would like to cover is first the AMOC reconstruction using what I call physical, with quotes, you understand why in a minute, surface nudging in a perfect model setup. Of course, nudging is not physical, you'll reply right away, but you can do it in a physical or an unphysical way, as was already shown by a couple of people. And then I'll show that in a perfect model setup. And then we'll move into the historical context by trying to reconstruct the observed decadal variability using surface and also a new way of nudging I alluded to yesterday about 3D atmosphere nudging. Then, of course, I'll have to show what we have done in terms of impact of volcanic forcing on AMOC variability. And the last thing, I mean, this will be really short, but maybe to finish the discussion, I'd like to propose something called the reconstruction MIP, or whatever we want to call it. And you'll see here that I'm using the word reconstruction, not initialization. Because our focus at IPSL has been really not so much on the hindcasts. Hindcasts you need to initialize. It's really about reconstructing. And this we feel as our expertise and scientific interest is much more in that aspect. That, we believe to make a proper forecast, you need to do a proper initialization, so a proper reconstruction. And this is the bit we've been focusing on. We're doing hindcast as well, but I won't be presenting too many of those here. Right. Oops, that's going too fast. Right, so these are things around this audience are obvious. I mean, the decadal predictability comes from understanding the role of external forcing, but also initializing the modes of internal variability, so the whole zoo of them. I think what we see in the literature coming out after CEMIT 5 is that the AMOC is really the dominant and the main source of internal predictability in today's decadal prediction systems. So it's really an important beast to concentrate, and I really believe, I mean, I heard Leon saying we shouldn't do AMOC in the DCPPC volcano. Maybe we can discuss that. But I think this AMOC it should be a central piece of whatever we do in Decadal, because that's our main source of internal variability. I mean, if you remove all the forced, you end up with it's not the only one. I mean, the PDO might do, but today we're not in as good a shape than the AMOC. Right, so the goal here is how to reconstruct the AMOC in the models. It's a challenge, as you know, because we have basically no observations of AMOC for the last decades. We have a few direct observations for the last years, maybe 10 years now, even less, to the rapid array. Models have errors, it's classical. Also, the historical record has the impact of external forcing. And if we're interested in initializing internal variability, that's a problem, because we don't know which is coming from what. The other big problem, and Alicia showed that Monday, that ocean reanalysis don't agree. This is an example of work by, oops, wrong button. Yeah, the work by Sulagna Ray, making the correlation, this is zonal mean, depth, and latitude, correlation between SODA and RS4 for the last 50 years. And basically, the region where they agree is down to 200 meters, maybe a bit in North Atlantic, but the rest, where all the decadal information would be, reanalysis don't agree. That's a real problem. What is the real ocean, what has been the real ocean in the last decades? Right, so to overcome a number of these issues, we decide to go in the perfect model world. And we're not going to do that just, stay in the model world. We like to use the perfect model world to come back to the reality. So, of course, the question how to reconstruct the 4D ocean, so the 3D plus time varying. In a perfect model world, we could use any data. That's the beauty of it. We have exact observations, everything. but we want to apply whatever we learned back to the historical context. So we cannot do anything we like. We also want to understand the physics of how we construct the ocean. Again, there's still that problem of signal-to-noise ratio. Historical period is too short to provide any robust statistics at the decadal timescale. I mean, we can discuss that, but that's really a problem. Also, the experience with ocean-only models we have at PSL and l'Océan is to not tamper with ocean internal dynamics using either another model or imperfect data. Hence, the decision we took very early on and to use only surface or atmosphere. We'll see data for the reconstruction phase. And it's not only that we didn't want to, you could say that surface nudging is a cheap way of initializing. There are fundamental reasons to also use just surface nudging. Right, so the AMOC in the model, very quickly. So it's a bit weak. I mean, it's 10 to 13 sphere drop amplitude. We have, and that's been a long work also we believe to be able to understand the predictability, you have to understand the variability, you have to understand the mechanisms of variability. So we have now a couple of very detailed studies that looked at what is giving us variability in the AMOC in that specific model, and that's model specific.
So by weaker than observed, that's compared to the rapid?
Yes. Yeah, and typically you have 15, 18 sphere drops AMOC. But, okay, it might be in the past it was weaker, or in the future it might be weaker, but it's not 5 sphere drop or 30. So, but. Right, so basically we understood there's a 20-year cycle in the AMOC. There's really, we have 1,000-year control simulation. There's a very nice 20-year variability, and we understand it quite clearly. Now it's a mix of the surface and a subsurface mode. I don't want to go into the details, but what is key is the convection. The model only does convection south of Iceland because it has it doesn't do much here or here. So that region of convection is basically joining up the surface mode and the subsurface propagating mode, has been shown in other studies. So now we have a pretty good understanding of the physical mechanisms driving that 20-year cycle. That's really important for the rest. Right, so this is some work we've done some years ago with a student at Knox. So, and the perfect model predictability, now we started from a long control pedestrian run, which is that black curve here you'll be seeing a lot. And we just took the initial state before some AMOC situations and see what we can predict in the perfect model predictability, things that George has been doing and others. So just focus on those three here, where we have an extreme peak in the model. So this is the 1 standard deviation, and you see that went above 2 standard deviations. So so interesting to see the predictability of this. So we started 15 years before the peak by just perturbing a bit the SST that the atmosphere sees for the first time step, so really very little perturbation, and doing 10 members. And we see that we do get the maximum, but not the extremum. If we start 5 years before the peak, we do get the extremum. Okay, so it's telling us there's some dynamics happening here that has different lags, and it makes sense. If you're starting from the extreme, then you're back into the climatology, and as Jay was saying, this is just, coming back after an extreme. So you might argue this is maybe a predictability that is, by chance. Or right, so then the question we've been asking ourselves, okay, can we reconstruct not the initial states, going away from perfect model predictability, can we reconstruct the AMOC of the model? And for that, going in the perfect model, we use a 150-year sequence of 1,000-year or 1,000-year semi-5 control run as surrogate observations. So this is those 150 years in blue with that extreme peak, okay, we're interested in. Then we take a restart after, and this is our original free run, and we're going to nudge the model with that, starting from that initial state, and several others you'll see after, but we start with this, towards the target SST, SSS, and also forced wind stress to see how we can reconstruct this AMOC here. That's the goal. This is nice here because we don't have any external forcing. We're not missing any data from observations. We can compare everything at every time step. We know the mechanisms by which this variability is happening. So we got rid of a lot of the problems we have in the historical context. Right, so we use the typical restoring with that restoring coefficient, which is corresponding to a 2-month timescale over 50 meters. This is classical. So this is physically based because it's basically the observed dq over dSST. And I think Christophe was showing that the other day. We also devised an equivalent gamma S for the salinity. And it's devised to have the same timescale than the 2-month timescale as well. Right, so in here I will show the impact of the salinity nudging that was also shown by Rim yesterday. Right, so here we're just nudging at the surface. So the first question, what can we reconstruct at depth? Yes, Noel?
You drive the model with the perfect wings, that one that's set on the previous slide, and the most wind stress.
Yes. Yeah, we take the wind stress. Actually, in the perfect model setup, that doesn't change much without the wind stress. Because you're in a perfect model, the TNS restoring is doing most of the job. We've systematically done both, but...
Are these monthly or daily?
This is monthly.
And do you adjust for the max min?
The max min of...
Because if you use the monthly mean with the interpolation that the model is going to use internally in time, you are not going to necessarily capture the actual monthly mean or temperature salinity. Do you adjust you're storing SSS and SST
no, we
to
haven't,
account
no.
for that? Because you'll lose some there.
Yeah, that's a good point. No, we haven't done that. I'm not sure it would have a large impact, but that would be interesting to test it, yeah. That's, right, so of course, because we're nudging the surface, we want to know what happens at depth. That's really the goal of all what we're doing. So these are correlation with the target in North Atlantic. In that paper, you'll see many other correlation in different places. So this is depth, saying at the surface. This is the mixed layer depth, 300 meters, 2,000 meters. This is the zoom at the surface. These are correlation along that axis. So 0 is 0 correlation, and then 1, you're perfectly agreeing on the 150-year time sequence with the target. Okay. Now we have 2 types of runs. Those with SST nudging only. These are the reddish things here. So, and that's for temperature, and that's for salinity. And then the one with SST and SSS nudging, the greenish types here. So what we see is, of course, when we don't do anything with the salinity, you restore in the mixture depth, which is what your nudging is doing, but you basically don't do anything below. To get the reconstruction below, you need the salinity. And this is for temperature. If you add the salinity, this is what the correlation you have to temperature, so now you're good for the first 2,000 meters. Okay? And of course, same thing here for salinity, and we have nothing in salinity when we just restore the surface temperature as expected. Right, so that's encouraging. And basically what's going on is that if you look at the mixed layer depth, which is really setting the way your forcing is going into your deep ocean, this is the reconstruction, so the correlation of the mixed layer depth between the nudge and the target with SST only and with SST and SSS. And again, this is correlation of 1. We do a much better job when we have the salinity, and it's not surprising because basically the SSS nudging is forming the right water masses and hence the convection at the right place. Now, if you just keep the temperature, your RC fluxes are going to create water masses at the wrong density. Okay, so you're going to be off balance. So the salinity nudging is essential to get that deep formation. But again, this is no surprise there. These are the model convection sites. So now if we go to the reconstruction of the AMOC, which is what we're interested in, so you have here the AMOC strength, the target in black, you recognize, and the SST plus SSS nudging. I haven't gone into the sea ice problem. You want to stay clear of sea ice. We can discuss that later, but that's really important. Otherwise, you have nightmares. So we have a pretty good correlation. Again, think we're just nudging with surface variables, and we recover a correlation for almost 150 years. We have those 2 peaks. We're missing the extreme. We'll go with that, but the correlation is 0.6. That's pretty encouraging. Okay. Right. Now we haven't reproduced that AMOC, the extreme, and this was our goal. We chose that period. We want to, represent that extreme. So let's see how we can do that. So now we're going to focus only on a few decades around that peak here. Right. So again, I'm using SST, SSS nudging, and wind stress forcing in the pre-industrial control. So that's work done by Pablo Ortega. So here I'm just focusing on the no Ekman part because we've seen the wind doesn't. When we go to the historical context, that'd be different. The wind, I'm sure, would play a role again. But here it's not a secondary role. So we look at the no Ekman part. So we've done a 3D nudging because we have all the data. As you know, some groups are doing 3D nudging or just to make sure that. So we start from here what we call adverse initial conditions. So not the exact initial conditions, but conditions that are far away from what the model has seen, the control model. And when we do the 3D nudging, not surprisingly, we recover everything perfectly. Okay, good. We know that that's the best we can do with this. Now, if I start with adverse condition and adverse initial states 15 years before the peak and use a constant gamma, so 2-month timescale, completely miss the peak. Not even a maximum. So we have no maximum, no extremum, and any initial state doesn't work. Okay, these are the 3 things we'd like to have the maximum, the extremum, and when we go back to the historical context, or we don't know what the initial state was 40 years ago, we need to be able to reconstruct whatever the initial state of the reconstruction. Okay, so now if I start from exact initial conditions, these are those red curves 15 years or 25 years before, I have my maximum. This is what we've seen with the, from the Precision et al. Paper. So this is no surprise. So now we get the maximum. Okay, the only difference is that we came to have the right initial state. That's good. We have some memory. The AMOC has some memory in it, but we don't get the extremum. Now, that's where we bring in the physical drivers of the AMOC and say, okay, we need to represent the convection in those sites. The mixed layer is doing a pretty good job already, but we need the precise convection details. Convection happens down to 2,000, even 3,000 meters sometimes in the model, and lasts for 2-3 months in winter. This is really short. And our gamma value here is way too weak to enforce this. So this is where we bring this idea of a variable gamma. Instead, we're varying the restoring, and what we're keeping constant is the 2-month restoring time scale. It's just a change of view. So if you keep the 2-month relaxation time scale, then your gamma, you can write the equations, becomes proportional to the mixed layer depth. Okay, so that's what we do. We introduce that variable gamma as a function of the mixed layer depth. And now we start again from those adverse initial conditions as the blue curve. Okay, variable gamma, initial condition adverse, and now we are able to get our maximum, even though we start from adverse initial, just by changing the relaxation time scale.
Do that both for temperature salinity or only temperature?
It's always temperature and salinity. Yeah, they work together. It's really important that.
What is the maximum gamma?
Oh, we reach several thousands.
So it's essentially order 1 or 2 days, then, right?
No.
Yeah.
Oh, sorry.
But it will happen in the very small region of convection during those couple of months in the winter. You'll get a gamma that reaches 2,000, so 1 day time scale. Yeah. But the rest of the time, when the mixed layer is shallow, you keep the 40. So you don't get into the problems that if you keep a constant high gamma that Christophe was showing the other day. It's you get the best of both worlds in a way. So. Right, so now if we start from the exact initial state, miracle, we get our extremum now. So here I take the exact initial state, 15 or 25 years before, and I'm able to get the extremum, not only the maximum, but the extremum. So here, with just surface nudging, we're able to reconstruct an extremum of AMOC. That was pretty cool. We're pretty excited when we found this, because that's really what was our goal. Right, and of course, this is the exact initial state. We're not, we'd like to have that last thing. So what we did, we started from adverse conditions, but further back in time to see if they would change anything. And if we start 25 years back in time with adverse condition, then we also got our extremum. Okay, so if we start far enough in the past, do a varying gamma, so keeping that 2-month timescale constant, then we can get both the maximum, the extremum, and initial state. So that's pretty encouraging in reconstructing the AMOC this way. Right, so now of course, what does it mean for historical AMOC, which is what we're interested in? 2 minutes? Wow, okay. Might be 5. I have too many questions. I mean, it's already. Right, so in theory, if we know, that's a big if, of course, if we know the SST, the SSS, and the wind stress since 1900, then we know the AMOC. Yep, okay, the unforced AMOC, which is already, quite interesting. Add the external forcing, and then we can have a reconstruction since 1900. There are big ifs, but at least it's not something that is, would be completely out of reach.
You need a spin up.
If the model is perfect.
You need a spin up, so it'd be 19, from 1925.
Okay, yeah, or you start in 1850, or, I agree, but yeah.
Are you done now?
First, that's not right, because you need to know what the gamma is in addition to that.
No, we know the gamma is automatically, the gamma is, we know, the gamma is not a physical observed quantity. It's a trick we're using.
No, but how much to restore to, you need gamma.
Yeah, but that gamma is automatically done. It follows the mixed layer of the model. I'm not. Yes?
Not in your,
Yeah, that's what, maybe I didn't explain it properly. But
when you did the perfect model experiment,
yeah.
you knew what the mixed layer depth was.
From the model.
From the model.
From the model, yeah.
But in this case, you do not know whether that's the true mixed layer depth or not. You need gamma.
No, but that's in a perfect model. In a perfect model,
No,
he
in
is a
perfect
state
model he
dependent.
knows, but
He's
now
a
he's
state
going back to
dependent.
the
No, I don't.
We have a state dependent gamma.
No, because I'm here. The model will produce. Okay, I'm going to start in 1900. Force my model. It will produce a mixed layer depth. It will produce a mixed layer depth, and I'll use that. It may be wrong.
Not the perfect mixed
No. And if the model perfectly reacts to this and creates the right mixed layer, and there are many ifs.
Yes.
But what I'm saying is that it's not something that that would be completely out of reach. Right, probably you need to require ensemble. We're in better shape for the recent years. This may be something we can try for the recent years where there's more data. And anyway, so I'll skip that. Just to move on the second point quickly. So we've been doing a number of nudging to try to reproduce the historical. So we have a classical CEMIT 5 SST anomaly nudging runs. So this is just SST. And then we've been doing 2 new runs with the 3D wind nudging towards era interim, using the U and V, so through the whole column, with a 6-hour restoring timescale. This is a feature in that is LMDZ and other models now can do that. And then we've done that with the 3D wind and the full SST. Here you cannot use anomaly SST because you cannot use anomaly winds. I mean, that's a, well, I won't go into the details, but anyway. So this is what we get with our historical runs. And this is the observations in red and the different observations. So we have a correlation due to external forcing, okay. This is with our nudge SST. We reduce the spread. We increase, as expected, the correlation with the observation, with nudging to the observed SST. And this is what we get with our new runs. So we start them at the, in 1980 because era interim only starts then. We have first 10 years where there's some adjustments going on. But after that, we barely see the difference with the observations. It's doing an amazing job at reproducing the variability of the observations because we're driving the whole atmosphere. Oops, that's not what I wanted to. Okay, pacemaker, I will skip it. It's just to say that we're finding some of the results that were presented when you do pacemaker in the Pacific or in the Atlantic. In the Pacific, it has you can recover the hiatus. If you do it with the Atlantic, it doesn't work, but so I'll skip that. Yeah, I wanted to show here the mixed layer depth of the control minus the Dubois climatology. So this is the historical run where we have quite large errors in those regions where we know the model doesn't have the right winds. When you nudge the 3D winds, you correct a number of those errors in the model. There still are a few, but they are a lot reduced. So that's also another way of driving the model, is driving the winds up aloft and not the wind stress. I'll pass that. Yeah. So, right. So quickly, the impact of volcanoes on AMOC reconstruction. So again, here, this is the AMOC in the historical runs, in the nudge runs. We have 2 peaks in 1990 and 1970s, end of the 70s and 90s. And the only thing common between those two is the external forcing. And indeed, if you put a volcano, Agun volcano, 15 years later, because the volcano is going to impact the surface here. So it's related to what one of the mechanisms, not the salinity mechanism, is the cooling, and not only cooling, but also advection of sea ice to the East Greenland current into the Labrador Sea. 15 years later, we have a maximum of the AMOC, and then 20 years later to the 20-year peak. Okay, so we have that 15-year maximum of the AMOC after a volcano. I won't talk about the other volcanoes. If you take all the semi-5 models that have 20-year variability, and look at the historical, they also have those two peaks. Interesting. And if you take reconstruction over the last 1,000 years, take 5 volcanoes that are within the range of the Pinatubo, and look at ice cores and Icelandic bivalves that are telling us about the ocean circulation, you also do find a maximum of AMOC 15 years after. So maybe there's some reality to this. All right. So in summary, reconstruction the ocean variability, particularly the AMOC, is absolutely key, I think, for all what we're trying to achieve here. It's challenging because of lack of observation, external forcing, there's internal variability, model errors, etc. And the perfect model framework is a great framework to overcome these limitations and explore the mechanisms. Now, I think with our model, we're in a much better shape to know what to do in a historical context by having explored these different techniques in the perfect model setup. So physically based surface nudging, where you're keeping the timescale constant rather than the restoring coefficient, is shown to allow the model to build a coherent internal trajectory and reproduce the AMOC variations, including extremes. So the analysis is still underway. There's some more testing to do. So that clearly could be something we could consider for the pacemaker experiments, where we're all doing nudging. That would be a more, maybe a more efficient way of imposing what we want to do. And the 3D wind nudging is a promising avenue for reconstructing the coupled system. And this is something we've always wanted to do. It's the fourth ocean of the rich, I call it, because we never, even using Bob formula is not satisfying. So now we have the whole coupled system and nudge the dynamics and let the coupled ocean atmosphere interface free, and the coherent physics, the coherent energy budget, the coherent water flux, water budget, etc. Right, so here one proposal is to have something like called the ocean reconstruction MIP. I don't know how to call it. The idea would be that we would select a couple of targets, probably reanalysis or core runs, or we have something we discussed. They could be either from 1900 or from 1950. And then we try by different techniques, so surface nudging, 3D nudging, mix of the two, anomaly or full field, to reconstruct the AMOC. And then, or not only the AMOC, we could look at other indices like ACC, the meridional heat transport, all those kind of things. And we could use recent ocean observation as validation. Of course, there's the issue of the salinity. And also that there are many groups starting reconstruction. We've seen a couple. I think it was in using the MRI model. We have a project at IPSL to also do a reconstruction of using our model, and this could be part of this there. And we would learn a lot on how, what the actual AMOC was doing a multi-model approach, and what's the best technique to use to reconstruct it and initialize our model. So I'll stop here. Thank you.
Yeah, I'm not quite sure what you asked. Isn't it sufficient to have a wind forcing to reconstruct the AMOC? I think that has been shown by
A wind forcing.
Carsten Edland years ago.
Well, if in the perfect model, no, because the AMOC is well, there's a bit that is wind driven, okay, obviously, but most of it is driven by thermal influxes. So if you don't get your water masses formation right at the right places, you cannot reconstruct your AMOC. So I mean that's it's,
John? I have a couple of questions. So first, I think you said that if you use SST and wind forcing, that you recreate the unforced AMOC variability. And I guess my question is, do you mean the non-greenhouse gas force variability? But even that would be in there, wouldn't it? I mean, surely if that's in the SSTs and the winds.
Yeah, that's a good point. Yeah, I guess I was. Yeah, maybe. Yeah, you're right. It would come through the SST and the SSS. Yeah, I hadn't thought of it. Yeah. Yeah. No, you're right. Yeah. I don't know why I wrote it. Yeah. Blame it on the jet lag. But,
and the other question was, so you showed that the errors in the mixed layer depth were reduced in
Yeah.
when you use the full SST and the full winds. But so you haven't done any predictions from that yet? Because
No.
presumably you get a lot more drift.
No. We haven't done, in all these, we haven't done hindcast yet. That's coming up. But really our goal was first to understand, what can we reconstruct of the ocean before. Because if you launch a hindcast and your ocean is not properly initialized, then, you get the forced predictability, but not the one coming from the internal variability. So.
Eric, you've been doing this SST nudging in the context of ENSA. It works very well in the tropical Pacific. So you can get a lot of subsurface information just by SST nudging, and you kind of, in the context of how much data you need, so it looks like it can fill in for a lot of subsurface data you may or may not have just by nudging the SST.
Yeah, I mean, what I didn't discuss here is that there's a latitudinal difference. We know the ocean works differently in the tropics and the mid-latitudes. In the tropics, the SST is enough to reconstruct the wind, the salinity, the freshwater flux, everything. In the mid-latitudes, you need the salinity. You don't need the salinity in the tropics for this. That's clear. I mean, Christophe has made a number of nice tests on what to nudge where, and that shows that clearly. So.
I was very surprised surface nudging can constrain the AMOC. So the point is a mixed nudging timescale depends on the mixed layer depth.
Yeah.
I'm just wondering, mixed layer depth is also very heavy bias in the real world compared to the model observation. So if we assimilate, if we use such kind of mixed layer dependent nudging time for real world, so model biases become much larger. So
That's a fair comment. We have to explore that. That's a fair comment.
how can you manage? You have some idea to manage?
No, we haven't thought yet. I mean, this variable nudging, we got the idea 6 weeks ago. We made the runs for this meeting, so we're very excited to reproduce at last our extreme AMOC. So I'm sharing this with you as a premium. We still have a lot to understand, and also you want to maybe distinguish if your delta T is the difference between the model SST and the observed or the reference SST is positive or negative, because it's not the same physics that you're dealing with. This is okay for when you have to cool. When you have to warm, if you increase too much your gamma, as Christophe was showing, you lose the connection, the high frequency connection between the SST and precipitation, for example. So we might have to do a asymmetric one, but there's still a lot of testing, and then of course going to the historical. I agree with that. That comment on the real mixed layer and the model mixed layer is a fair comment.
No.
So I think it makes all sense to me. I think it's very nice. But I think the biggest challenge here is that in models, there's no agreement on the mechanisms for atlantic multi-decadal variability.
No.
So it's difficult to see how we will use our current set of models to do something like this that will make sense in the real world.
Okay, but what I'm saying is that if you want to use your coupled model to reproduce the last decades and do hindcasts, you're reconstructing the AMOC. And knowing, so now here you're just replacing the observations by some well-known 4D target. There is not, we don't have observation. If we had observation, we would take that but so I agree, reproducing a model with another model can be tricky, but is that they understand?
It would be interesting to compare this with the core force graph, because what you're doing is essentially constraining buoyancy fluxes. Yeah. I wonder how we compare the core force.
I agree. That's why I put the core runs here as well, because I think that in a way their internal dynamics is coherent, and there's a lot of evidence that they agree much better together, all these core runs, than the different ocean analyses that nudge in some way 3D information. Yeah, I agree. That's
Okay, to George, then
If I understand your suggestion here is that if you're going to do hindcasts, it's best not to involve any actual observed ocean data. Simply use this. And is this
in this deep ocean?
Is this because you think you'll actually do yourself harm?
Yes.
Or is it because of some initialization shock?
I think because we don't have enough observation, you do yourself harm. But that's, I mean, and again, the experience of ocean-only runs we've had, been doing for decades at l'Océan, at PSL. And if Gervan was here, he would talk for hours on this. Work on the forcing, you'll compare your ocean. The tropics, it's obvious. Work on the wind, you'll get the exact tau observations. This is something you'll never achieve with 3D data simulation. The mid-latitudes is a different physics, but it's the same. If your ocean model is perfect and forcing, but the physics in the ocean model is pretty good. I mean, the first order for what you're trying to do, I think all the mechanisms are there. Okay, there might be some things, but and if you're forcing, you're forcing hard, you get the observed ocean circulation. Whereas we know if we put information at depth that is not coherent with the model or even current between themselves, the first thing your model is going to do is get rid of that. And it's going to take 10 years, exactly the time scale you're interested in.
So it's mainly the shock here.
It's the shock. Yeah.
So
yeah.
we set up the next talk and take the issues.
So just remind me one more time, you're doing literally only adjustment of the surface, so you're not doing any covariability with depth, nothing like that.
No.
And then the other thing is, so you kind of highlighted the importance of sea surface salinity, which is not very well observed.
No.
So there's an issue with actually using this. And then the other one is in reference to the core set. So they do show this, that they have more agreement, but you also show that having the right variability of the SSS may be key. And in core force ones, those are restored. Well, a lot of them have salinity restoring, and that damps the SSS variability, right?
Yeah.
So does that suggest that maybe the core force runs are underrepresenting AMOC variability?
Possibly.
No, I disagree with that. The different salinity restoring, when we look at the variability in the core 2 paper, you cannot tie it to different salinity restoring or reduction in
The mean or the variability?
the variability. So the thing is that
Depends how strong the restoring
depends
is.
upon how strong the restoring is, but they're ranging from 50 days to 4 years over 50 meter length scale.
Yeah, but this is much stronger.
Yeah, so in this,
Yeah, but this is a climatological restoring.
Yes.
So that damps, and you're
No,
actually
no.
exciting
Yes.
the SSS with your restoring.
So what one want to do is do the same with that increased gamma, but having a climatological SSS restoring to see what happens.
Okay.
If we kill the AMOC.
Thank you very much.